Welcome to day 24 of the 2023 Advent of Code. So for today's problem, we are in a hailstorm. Our snow machine isn't working and it's been creating hail instead. We're going to see if there's something we can do to break up the hailstones. So the hail is behaving magically and they're all flying in perfectly linear trajectories at a constant velocity. We're given a bunch of lines indicating each hailstone's current position and its velocity as an x, y, and z vector. For the first part, we're going to see if it's likely that the hailstones will actually collide with each other and break apart into tiny ice crystals, in which case we won't actually need to smash them apart ourselves. To estimate this, we're first going to ignore the z-axis entirely. So for part 1, the z values, both the z position and velocity, do not matter whatsoever. So just considering the x and y axes, we're going to see how many of the hailstones' paths will intersect. The hailstones don't have to collide. In other words, they don't have to be at the same point at the same time. We just want to see if their paths will intersect. So in this example for the test data, we're just going to look for intersections that happen within an x and y position of 7 to 27 as a minimum and maximum. In the actual test data, we're going to have much larger values for both of these. So this is the result of the comparison. We see that some of the intersections will not occur at integer points. So these two will collide, these two will also collide. In this case, they collide outside of the test area. These two do have a collision if you draw them as lines, but the paths crossed in the past for one of the hailstones. In other words, it's behind its current position, so it would have been there at a negative time. Some hailstones' paths are also parallel and will never intersect, and so on. So for this problem, I'll show you an easier and a harder way of doing it. So look at the harder method first. We're going to do some math to figure this out. So we're going to convert each hailstone into a line. And the way we're going to do that is we're going to represent it in standard form, which is in the form ax plus by is equal to c for some constants a, b, and c. So how do we determine this? Currently we have it in parametric form, where we can say that each point that is on the line will be of the form x plus tvx, y plus tvy, where x and vx are the starting position and the velocity in the x direction, and y and vy are the position and velocity for y. So in other words, for some input parameter t, which can be any number, all points on the line can be represented as essentially the starting point plus some amount of time multiplied by the velocity vector. So that's essentially what we're getting. And so we want to convert this into standard form here. To do this, we're going to want to find some sort of equality for any given point on the line. So let px and py be random points. We'll set a condition such that this is on the line. The condition to this is basically that px is equal to x plus tvx for some variable t. And likewise for y. And so if we rewrite this in terms of t, we get that t is equal to px minus x over vx, and is also equal to py minus y over vy. So this t just needs to exist, it doesn't matter what its value is. And so if we ignore it, this is our equation for a point on the line. So in other words, a point px, py is on the line if and only if this condition is true. If we rewrite this to get rid of the fractions, we'll have vy times px minus x in brackets equals vx times py minus y. And so if we rewrite this and refactor these out, we get vy px minus vx py, bringing this product over to the left, is equal to, and then we bring this over to the right to get vyx minus vxy. So in other words, this is in standard form because px and py are our variables, and our constants are vy, negative vx, and this here. So let's get to the conversion part. So we can define a hailstone class that will accept a couple of arguments, the x, y, and z position for the starting position, and the x, y, and z for the velocity. And right now we'll just store all of these. Okay. And then we'll also store the a, b, and c constants, which we can get using this formula here. So self.a is equal to vy, self.b is equal to negative vx, and self.c is equal to vy times star x minus vx times sy. And so now we can do for each line in the input, we're going to replace the @ sign with a comma, which will give us something that when we split by commas, we'll get a bunch of integers with a bunch of spaces around, but we don't need to care about the spaces because the int function automatically removes them. So we'll split by a comma, and then we'll say list, and then we'll say map int over this, and this will give us our hailstones. So right now we just get a bunch of map objects. And so now what we can do is we can call the hailstone constructor to create a new object. And we'll use the star operator to split all of these arguments, split the map across all of the arguments. So this is equivalent to passing in the first through sixth values independently. And so now we get a bunch of hailstone objects. Let's represent this a bit more nicely using a representation function, and we can make it return like hailstone and then we can insert our variables. So we can say like a equals self.a, b equals self.b, and c equals self.c. So now we get these as our lines, and these are all in standard form. Now we want to find an intersection point. So given two equations, a1x plus b1y equals c1, and a2x plus b2y equals c2, we want to find an intersection between these. In other words, we need to find some x and y that satisfy both of these. So first, let's check if they're parallel. If they're parallel, that means that their slopes are the same. And the slope is the rise over run, so it's either a1 over b1 or its reciprocal, I forget which one. But basically the long story short is that if these two values are equal, then then these two lines are parallel. And so if they're parallel, we can just skip them. So let's start going through our hailstones. So for I hailstone 1 in enumerate hailstones, for JHS2 in enumerate, or just HS2 in enumerate hailstones up to I. This just prevents us from checking the same hailstone against itself, and also prevents us from checking two hailstones in both directions. And so if these two are parallel, let's print if they're parallel. So if hs1.a, and to avoid floating point errors and also zero division, we're going to cross multiply like this. So if a1 times b2, let's rewrite this like this to make it a bit simpler. So a1, b1, c1 is hs1.a, hs1.b, and hs1.c. Okay, so if a1, b2 is equal to b1, a2, then we can print out our hailstones. I forgot to remove this enumerate. Okay, so these are the only set of hailstones that intersect. Let's check what their actual values are. So if we print hs1.x, y, and z, and the same for hs2, we get that the intersection is, Sx. We get that these are the points. So if we go here, we can check that there is only one set of lines that are parallel, and it is indeed this pair of points that we observe is parallel. So if they're parallel, then we just skip this step. Otherwise, we'll move on to finding an intersection. So we're looking for some x and y that satisfy this equation here. This system of linear equations. So let's solve for x first. To solve for x, we're going to get rid of the y variable. So let me just copy this over here for later. So solving for x, we want to eliminate the y variable, which we can do by making them equal in both equations. So we'll multiply the top equation by b2. We get a1 b2x plus b1 b2y is equal to c1 b2. We multiply the bottom equation by b1. And we now see that these two are equal. So now when we go to subtract the equations from each other, they cancel out. And so when we take the difference of these equations, we get a1 b2 minus a2 b1x is equal to c1 b2 minus c2 b1. And so x is therefore equal to c1 b2 minus c2 b1 over a1 b2 minus a2 b1. So this is now why you see it's important that these two aren't equal. If they are equal, then this value is 0. And so this would be undefined as a result. We'll apply a similar tactic to solve for y. We'll eliminate the x variable. So we'll multiply the top equation by a2. And the bottom equation by a1. And this will give us a result of a2. If we subtract them in this order, so we subtract the top one, a1 b2y, a1 b2 minus a2 b1, y is equal to c2a1 minus c1a2. And so y it's almost the same thing, but the terms are reversed from each other. Over a1 b2 minus a2 b1. And so we can say x is equal to c1 b2 minus c2 b1 divided by a1 b2 minus a2 b1, and y is equal to c2 b a1 minus c1 a2 over a1 b2 minus a2 b1. And so now if we print out x and y for each set of hailstones, we see that the values line up with what we're expecting. So for the first intersection, we have 14.3 and 15.3. For the second one, we have 11.6 and 16.6. Third one is 6.2 and 19.4. Fourth one, it doesn't tell us because it's in the past, and we skip the parallel one. And then we have -6, -5 here. This is one of those past points, etc. So these are not in the same order as these ones, but we see that the values line up, so they're roughly correct. And so now we need to check if the points are in the past. To do this is actually very simple. We just take a look at the intersection point and the starting point and see if this has the same sign as the velocity. So if the velocity is positive, this needs to be positive. We need to end up greater than where we started. And if the velocity is negative, this needs to be negative. And so since we know that obviously multiplying two negative numbers gives us a positive number, we can just check that this is not negative. And we want to do this for all of the coordinates in case some of them are 0. But if none of them are 0, if we're guaranteed that, which I'm not sure if we are, we actually only need to check one set because they'll all be tied together. And so to check that, we just say that x minus hs1.x times, hs1.startx times hs1.vx must be greater than or equal to 0. And then we want to check this for all of the coordinate values. So this also needs to be true for y, and this also needs to be true for z. This also needs to be true for, sorry, I forgot we're ignoring z. This also needs to be true for hs2, and so instead of copy pasting, we can just say if all, this is true for all hailstones. And then we can just replace this with hs. So now we say if for both hailstones it's in the future, then we'll increase the total by 1. And now finally, the last thing we need to check is that this is actually within our boundaries. So if x7 is less than or equal to x less than or equal to 27, and same goes for y, then we add 1 to the total. And now to run this on our real input, we just need to replace our numbers with these ones here. It would appear that I accidentally put an extra 2 there. And now that gives us our answer for part 1. So I said there was an easier option than this, actually. And the easier option involves using a Python library known as SymPy, which stands for Symbolic Python, I believe. It's a symbolic math library. So what symbolic math means is, unlike how computers traditionally do math, instead of storing the numbers as like binary values, it stores them symbolically. So it has a precise representation of it, and it can perform exact math. This completely removes the possibility of floating point errors, but that's not what we're going after here. It's mainly the fact that it can also solve systems of equations on its own. And so what we're going to observe here is that we can skip all that converting to standard form thing, and we can just observe this part that we had from earlier. Remember the condition we used to derive the standard form. We had px minus sx over vx is equal to py minus sy over vy. In other words, the slope from the starting point to the intersection point must be equal to the ratios of velocities. So let's get rid of most of what we're doing here, and we just want a tuple. So the way we're going to do this is we're just going to say for I hs1 in enumerate hailstones, for hs2 in hailstones up to I, we do start x1, start y1 blank, vx1, vy1 blank equals hs1, and then the same goes for hailstone 2. So that gives us our positions and velocities for both. And so now we just need to solve for a px that satisfies this equation for everything. So let's import SymPy. Note that importing SymPy is a bit slow. This program is not that inefficient, but I better have SymPy installed. I do. Okay, Pylance just can't detect it because I'm using Windows Subsystem for Linux. To do this, we'll create two symbols, px and py. And we'll use sympy.symbols to get our values. So if we print that out, there's not supposed to be a star there. We get, it outputs them as the strings px and py, but they are SymPy symbols. And by symbols, I mean basically just mathematical variables. So now we need to solve for some equations. So we'll say answers equals sympy.solve. And to solve, we'll feed it a list of equations. And these equations are going to be more like expressions, really. All of the equations are going to be of the form something equals 0. So here, the real equation is px minus sx over vx Actually, let's cross multiply it. I don't know if there's a point, but it looks nicer to me. So this is what our equation is. But SymPy can't really work with this if we feed it like so. And so we're going to subtract and say equals 0. And so when we feed it in, instead of an equation, we're actually feeding an expression. And so our requirement is going to be we'll need to do this for both hailstones. So instead of separating the variables out, it's probably a bit easier if we do this for hailstone in HS1, HS2, and then we'll unpack the hailstone as SX, XY, and VX, VY. And our equation will be VY times PX minus SX minus VX times PY minus SY. So now if we print out answers, this is what we get. Sometimes it's empty, because sometimes there are no answers. And so if answers is the empty list, that means that the lines are parallel, and so we continue. Otherwise, we can say x, y equals answers px and answers py. Note that it's not a mistake that I'm not quoting this as strings. The keys are actually the symbols here and not the names of the symbols. And so these are all of our intersection points, and now we just need to check if they're in the future and within bounds. So if 7 less than or equal to x less than or equal to 27, and 7 less than or equal to y less than or equal to 27, now we check if they're in the future. So if all x minus sx times vx is greater than or equal to 0, and y minus sy times vy is greater than or equal to 0 for x sx x sy blank vx vy blank in HS1 and HS2, then it is in the future for both of them. So print xy. And so we just get two valid intersections here. .eval_f will evaluate it to a floating point number, so this will turn them into real Python numbers, which are imprecise, but it tells us that these are the two intersections we're expecting. So this solution runs slower because importing SymPy takes a bit of time. It's actually not that bad, but it is much simpler of a problem. You don't really have to do much thinking. You just need to find these two equations, and they don't even need to turn it into linear form and look for a smart way to solve it. You just say, hey, SymPy, solve this for me, and it'll just give you the answers. Before we move on to part 2, I wanted to take a moment to talk about Codecrafters. Codecrafters reached out to me to discuss a collaboration with my channel, and I took a look around and immediately fell in love with their product. Essentially, Codecrafters is a platform for learning advanced programming concepts by working on challenge projects, and as someone who's always been a proponent of learning by doing, I truly believe that this is by far the most effective way to learn how to code. I've been using it to learn Rust, which I've been wanting to do since last year, but I could never find the motivation. However, it's excellent even for languages that you're already proficient with, as there's always more to learn and always more you can do to level up your skills. If you're just getting started with a language, you might also be interested in checking out exorcism.org, which is a 100% free and open source platform for learning programming languages, with absolutely no prior coding experience required. The development environment is also extremely nice to use. Once you've selected a project you want to work on, all you need to do is pick your language, answer a couple of questions, and then you get a Git repository created for you. And you can just clone it, code with your normal setup, and once you're done each stage, you just push it and Codecrafters will test your code and give you feedback. If you're stuck, they also have community discussions under the stages, and code examples if you're really stuck. There are also many perks you can get with a subscription, such as discounts on things to help you in your career, free trials on software services, and more. If you're interested, check them out using the link in the pinned comment and get a 40% discount on an annual subscription. Most tech companies offer learning and development growth funds, and will probably pay for something like Codecrafters. So it's an amazing opportunity to learn something new, improve your mastery, or whatever else. Plus, it helps support the channel. Thank you very much, and with that said, let's move on to part 2. For part 2, this is a lot more complex. So it looks like none of the hailstones will actually collide, and so we need to fix that. We need to get rid of the hailstones ourselves. We find a rock, and although it seems unlikely, if you throw it just right, you should be able to hit every single hailstone in one throw. So you can put yourself at any integer position you want, and throw the rock at any integer velocity you want. Including the z-axis in our calculations, we'll throw the rock such that it perfectly collides with every hailstone. So now we're not just looking for path intersection, we're looking for an exact collision. The rock also won't slow down or change direction when it collides with a hailstone. The way we're going to do this is by using SymPy. There is definitely a way to do it yourself, but it's just way simpler to use some sort of linear algebra solving library instead of trying to figure it all out on your own. The way we're going to do this is we're going to, for each hailstone, formulate a set of equations that must be met by the position and velocity of our rock. And so, looking at just one dimension, if we consider that our hailstone starts at xh and has velocity vxh, and our rock has coordinates xr and velocity vxr. The nice thing about this problem is that we can keep all of our coordinates separate for a bit until we need to equate them to each other. And so the amount of time that it takes for these to collide, we see that after some given time t, and in this case we actually care about t because these rocks, the rock and the hailstone do actually have to collide, we need some t such that xh plus t times vxh, so the starting position times the velocity, has to be equal to that for the rock. So the starting position of the hailstone plus time times the velocity must be the same as for the rock. If we rewrite this a bit, we get that tvxh minus tvxr is equal to xr minus xh, and so t is equal to xr minus xh over vxh minus vxr. And so we see that, of course, this has to be true for all of the other 3 coordinates as well, all of the other 2, I guess. And so this must also be the case for y. And it also must be the case for z. And so now we can stop caring about t. And so essentially we're looking for some xr and vxr. Sorry, that's an h. My writing is too messy. Yr and vyr and zr and vzr for the rock, such that it satisfies this equation, which will split apart into 2 equations, for all of our rocks. Now the problem is that we have 300 hailstones. And the issue with that is that the solver will take a long time to find a solution. What we can instead do is assume that we don't need to actually check all that many hailstones to find a unique solution. And don't worry, this solution won't make any assumptions. It will just be slower in the general case, but faster in this specific case. So first, let's get rid of most of what we've done. And now we're going to look for equations. So for each hailstone, for s, x, y, and z, and v, y, x, y, and z in hailstones, we're going to construct the equations that we want to add. And so first let's get our rock positions. So we can do rx, xr, yr, zr, vxr, vyr, vzr is a bunch of symbols. these are our SymPy symbols. And now we just need to add our equations. So equations.append. The first one is going to be, let's cross multiply again. So x r, I'm writing them without subscripts to make it easier to copy the code. So xr minus xh, which in our case is called sx actually. So sx times vy minus vyr is equal to yr minus yh times vx minus vxr. So let's represent that here. We have, and again, we're going to take the difference so that equals 0 so that SymPy can solve it. I think SymPy can solve it if you feed it a SymPy.eq. I think that works as an equation, but let's just do it this way. So xr minus sx times vy minus vyr minus yr minus yh, sorry, sy times vx minus vxr. And now we do the same, but between y and z. And if these two are equal, if the x and the y are equal and the y and the z are equal, by transitivity, the x and the z must be equal. So we don't need to add an extra constraint to check that. And now we can print, we can say answers equals SymPy.solve equations. And so we can print out our answers. And for the test data, this resolves very quickly. For the real data, this is going to take a long time to run because SymPy will spend a lot of time trying to figure out an equation to and a solution to this very large. I was completely wrong. I should never have doubted SymPy. That was actually much faster than I was anticipating. But we can also try with fewer lines. So we see here that it finds multiple solutions actually. Now, most of these are non-integers, and so we can say answers equals solution for solution in SymPy.solve equations. If solution, we're looking for all of them to be. So if all x is an integer for x in solution values. And so there is actually only one integer solution that we find here. But just in case this isn't always true, what we can do is if the length of the answers is exactly equal to 1, then we can break. Now we want to make sure we have at least 3 lines here first, because otherwise we'll find way too many different possible solutions. And so we can say for I, this thing in enumerate hailstones, if I is less than 3, sorry, less than or equal to 3, then continue. Wait, should it be less than 3? If I is 0 or 1, it's less than 2. If it's less than 2, that means that we've only inserted at most 2 hailstones into our equation set. And so beyond that point, we can start just checking when we find an answer. And once we find exactly one answer, we just need to print out the sum of the beginning coordinates, xr, yr, and zr. And so that does run a lot faster because we no longer insert all 300 hailstones. We just need to insert 3 in this case. If you don't check for the integer here, you will eventually still find an answer. In my case, it took 4 if you don't. So actually, just out of interest, let's print I as well. So here stopped on index 2, which means we inserted 3 hailstones. If we remove this check, then it stops at index 3. So once we hit 4 hailstones, there is exactly one solution, even if we don't consider whether or not it's an integer solution. But in any case, this gives us our solution for part 2. Yes. So there's most definitely a smarter way to solve this by figuring out how to work around with these equations yourself, but this is just a much nicer way of doing it. And other languages probably have similar libraries, but I'm not sure if they will work as nicely as this. So unfortunately, today's solution from me is a bit Python specific, but hope you learned something anyway. And in any case, thank you for watching, and I hope you enjoyed.